Hello, I wanted to study heat transfer and its application to design. Heat transfer is very important for designers because very often we're trying to get rid of heat or add heat to something. For example, electronic devices require the designer to design features that get rid of heat produced by the battery or other systems, and other devices like the handles of tools and such, you want to feel warm when they're touched, so you want heat to be added to them quickly. You see heat being added to homes to heat them, but typically in many industrial design applications it's electronic devices that need heat removed from them so that they operate more reliably and have higher durability. So if we look at some of the principles of heat transfer, it helps us incorporate things into design that amplify heat transfer. So there's sort of 5 heat exchange systems. 3 are heat transfer, which are driven by temperature differences, and then there's 2 orphans. So the 3 types of heat transfer that are driven by temperature differences are conduction, convection, and radiation. And then there's a heat exchange mode that's driven by pressure difference called mass transport, where molecules are physically moved rather than the energy of the molecules. And then finally there is a heat generation. So you can have heat generation due to chemical activity, due to friction, or biological systems can generate heat as well. So these things produce heat. And so those are the 5 categories that we'll look at, and I'd like to do them in reverse order. If we look at heat generation, that's the one that's easiest to understand. Basically, many things have little furnaces in them through chemical reactions or through resistance and wiring, or as I mentioned, biological activities. You get waste heat, you get heat created. And there's not much more to say about that, but heat is created. You see it most commonly with batteries. And there you get this heat generated that you have to get rid of. When you charge batteries, you feel them warm up. And when you run electronic devices, you feel the consequence of resistance in the wiring in the form of heat. And a toaster, for example, is perhaps the ultimate example of that. Then you have mass transport, which is something that's driven by pressure differences. So if you have high pressure air, it wants to move into the low pressure area. If that high pressure area happens to be hot, the hot air will move into the cold area. And this is akin to bringing in buckets of hot or cold air into a room. If you bring in buckets of hot air, it will heat up the room. That's mass transport. You're moving molecules. So if you open the window in your car, the air comes into the car by virtue of pressure. You see this in homes too, when you feel cold air leaking in through windows or doors. And houses are in the midst of wind, and that produces aerodynamic forces on the house. You have a high pressure side of the house and a low pressure side of the house, and you get air being drawn into the house or exfiltrating from the house. And that's an example of mass transport. If you open the front door and it's cold outside, that cold air might want to come inside the house, and it will only do it if there's a pressure difference, assuming there's no wind. And cold air is denser, and therefore it has a different density than the warm air in your house, and you'll get a convective cycle to flow as a result of that. It's fairly small, but it's there. When air rises as it heats and becomes less dense, the lower density is the motive force for the air to move. And the more it moves, the more inertia it has, and you get the stack effect, this phenomenon in which tall structures get fairly fast velocity of air flowing through them. And that can work with mass transport. So if you get air rising quickly, you have sort of the vacuum cleaner at the bottom of the column of air that pulls in air. So anyway, mass transport is moving air molecules. I'm talking about the air, of course it can apply to anything, but that's just a good mental image for it. Now the other 3 heat transfer methods are driven by temperature difference, and they are conduction, convection, and radiation. All of those are driven by not only temperature difference, but area too. So if you look at conduction, which is a surface-to-surface exchange of heat, the amount of heat transferred due to conduction is the temperature difference times the area times the resistance to flow, or actually the inverse of the resistance to flow, the thermal conductivity. So if something has a lot of insulating abilities, there will be less heat transfer by conduction. So, for example, air is a very poor insulator, so heat doesn't travel through air by conduction very well. And if you have a really good insulator like fiberglass or an oven mitt or something like that, you can touch things that are hot because even though the area is large and the temperature difference is big, the thermal conductivity is very low. So that's kind of the straightforward heat transfer. Most people are familiar with conduction. If you put your hand on a stove, you feel conduction very quickly. And you perhaps did that when you were 4 and never did it again. Convection replaces the thermal resistance form with a thing called convection coefficient, which is basically velocity. So convection is due to flowing fluids, and the faster they flow, the more convective heat transfer you get. And when we looked at fluid dynamics, you have an issue with the boundary layer that comes into play here. So if you have a thin, turbulent boundary layer, you get better heat transfer by convection. And that's a bit of a complicated topic to look at as a heat transfer issue alone. You have to go back to fluid dynamics and get your fingers wrapped around that. But basically, a turbulent boundary layer is thinner, and you get a higher velocity profile near the surface, you get better heat transfer. But you can find out these convection coefficients, you can look them up for a lot of real applications. But basically, high velocity increases convection coefficient. And that's why you put fans on car radiators and heat sinks and computers and things like that, to increase the air movement and therefore increase the convection coefficient. Because air doesn't conduct heat well, it needs to be aided by convection, to think about it in a simple way. Whereas water does conduct heat very well. So water-cooled things tend to come in smaller packages. You can get rid of more heat, or get rid of the same amount of heat in a smaller package. And you might think about that with computer electronics, where there's some spot cooling systems, and some of those are actually using the Peltier effect, which we won't look at here, but that's like in thermoelectric refrigeration systems, you can use a solid-state device to actually produce cooling by electricity directly, but that's something different. Radiation is probably the most complex thing to understand. You're very familiar with it because you feel the sun shining on your face and you feel good. You feel that heat, and it's being transmitted all the way from the sun, a long way. So you can move energy by virtue of electromagnetic radiation. And there's different frequencies that we're interested in. I mean, for humans, we think of the lower frequency infrared heat as being heat energy. The sense is heat. Then as you move higher in the frequency, you get visible light. And as you move higher in the frequency, you get UV, which kills things, degrades fabrics, and has deleterious effects along those lines. But typically in the design world, you're interested from UV to infrared because you're interested in degradation of materials, and you're also interested in the sensation of heat, and you're certainly interested in visible light. So some windows, for example, can be transparent to visible light, but opaque to infrared light or UV light. And you can actually put treatments on them to keep them from emitting heat. And there's a lot involved with radiation, so it's really important. So you've sensed radiation from the sun, and you may have sensed radiation, at least in cold climates, from a cold garage floor in the middle of the winter where it just draws heat away from you. So when you have a vacuum, the only way to exchange heat is through radiation. But even air, as I mentioned, is not a good conductor, so radiation becomes really important in air systems as well. So radiation has several properties associated with it, and it's actually interesting to look at the Earth and the Sun, because that's a kind of helpful model where the Sun produces radiation, and the Earth is irradiated by the Sun. Some of that radiation coming in from the sun warms up the air directly slightly, but most of it hits the ground. Hits the ground, warms up the ground then re-radiates back to the clouds, and you get this kind of dynamic with things being irradiated and then in turn radiated. So if something is above absolute zero, it radiates. And its propensity to do that, again, is a function of the temperature difference. So if the Earth is warm, and outer space is very cold, you get a lot of radiation from the Earth. If you throw some clouds in between, or even a lot of water vapor, or air even, that reduces the amount of radiation. So on a clear night, the temperatures get much colder because the Earth can radiate freely to outer space. But when you have cloud cover, that temperature difference is much less, so you get much less heat loss. And then the Earth gets colder and colder and colder, but alas, the sun rises and starts the process all over again. So it's sort of the give and take on radiation. So I hope that kind of gives you some insights into radiation. It's complicated because things are radiating back and forth to each other. Unless something's at absolute zero, it is radiating. And it's also complicated because it works across, or the properties work across the range of the spectrum. So something could radiate well at infrared, but not radiate well at visible light. And if you look at then another layer, and this is something that most of us are intuitively familiar with, there's a propensity to absorb radiation. So you think of dark objects absorbing radiation much better than light objects, and that's very true. So if you're south of a certain latitude, you should be painting your roofs white, or in commercial applications especially, paint the roofs white or with some sort of luminized paint to reduce the absorption of heat energy, so to reduce your cooling bills. In the same vein, if you're living in the north, especially in a house, you should paint things black to increase the absorption of energy, to decrease your heating bills. So you can use color to affect radiation, and that's a real powerful thing for a designer. Now, there's three properties in play initially. There's absorption, reflection, and transmissivity. Those three parameters have to equal 100%. So if I'm being irradiated by the sun, that energy is broken basically into three parts. It can be absorbed, it can be reflected, or it can transmit through me, which isn't going to work. But it does work well with windows. So if I absorb energy very well, like I have a dark shirt on, it's going to absorb energy very well, therefore it's reflecting very poorly. And you're probably very familiar with color theory, so you understand about how colors reflect certain frequencies, and black, for example, doesn't reflect well at all. White reflects all frequencies. So absorption for opaque materials, absorption and reflectivity are opposing numbers. High absorption means low reflectivity, and vice versa. So then too, you have transmissivity. If something is transparent, say if it's perfectly transparent, then you have no reflection and no absorption. Real objects tend to have a little bit of absorption and reflection. And of course, we're talking about different frequencies. So as I mentioned earlier, you can look through a window, so the visible light is transmitted through a window, but it could be opaque at infrared. And you don't care because you don't see it, your retina doesn't respond to infrared frequencies. So you can use that to your favor. So and also I should mention emissivity, which is a propensity to radiate outward, is equal to absorption. So if something absorbs well, it radiates well. So the classic example is a black body radiator, where you absorb 100% of the energy that hits, and you then can emit 100% of the energy that you have by virtue of your temperature being above absolute zero. A little bit complicated, but fundamentally you can use color to your advantage. That's what it amounts to. And two, for heat transfer, for radiation, it's strictly a surface property, so it's kind of cheap to get improved emissivity. And it doesn't have to be black that emits very well. A good example are low emissivity windows, which are clear, but they still have their emissivity altered by a surface. So there's a lot of material science issues at play here. And for example, you see that in clothing. If you wear black clothing and you don't want a lot of heat absorption, such as in much of the Muslim world, there's a whole science involved with creating black fabrics that do not absorb very well, and it can be done. So it's not just color. There is another layer there that gets kind of deep, but it's an intrinsic property of the material as to whether it absorbs or reflects. So it's part of the tool belt that you have. Then too, with radiation, you have to think about working along with other heat transfer methods. So for example, if you're trying to make a heat sink that is really efficient, you want a lot of surface area. You know that. And if the temperature you're working with is fixed, for example, your smartphone is running at 100 degrees and the air temperature is assumed to be 70 degrees, you have a 30-degree Fahrenheit delta T. Well, you can work with convection in a couple ways. By trying to encourage high velocity, which is hard to do on a smartphone. You can try to trip a turbulent boundary layer. Those things will help with convective heat transfer. Of course, conduction you get with your hand. So if you're holding a smartphone, there's heat exchange going on. If your hand is warmer than the phone, the warmth of your hand goes into the phone. You can reduce that with insulators. You can reduce that by area, so there's fewer contact points on the phone. So there's a lot of little tricks you can do with that. And that can work with radiation issues too. So these things all kind of get mixed together. It's an interesting field, and you can see it overlaps into fluid dynamics too, because when you look at convection, you're looking at, it applies directly to heat transfer, so you're looking at convective heat transfer issues. And I hope you find that helpful. Thank you.